Hi, everyone. I'm Diego with LinkedIn. And today we're going to be presenting what is Galene, our new search architecture. It's a project that started in half of or mid-2013. I'm going to tell you a little bit about how it basically empowered the engineers, the search engineers at LinkedIn to build beautiful things. But first of all, let's start with LinkedIn vision. Our vision is to create economic opportunity for every member of the global workforce. And the idea is that we want to allow everyone to be able to find work, to realize their dream job, and to be great at what they do. And in order to do that, we need to provide insights that usually come in a form of either search results to be able to find what you need to be successful, or recommendations. Maybe you don't even know what you're looking for, and search is a great way of actually realizing that. So search and recommendations are actually core to our vision. In this talk, I'm going to be talking a little bit about how we had to scale our infrastructure and how it basically made us more productive for developers on the search organization, and also how this new architecture made it easier for the result quality to actually improve. And what I want to say about infra scaling is that early on 2013, we were basically running through a wall, against a wall. We knew that at some point in 2014, we would have scalability problems, that the solutions we had in place wouldn't basically allow us to serve our members the way we want, and we had to do something about it. And the reason why we got to that point, and we had to basically rethink the entire architecture, was that for 10 years or so, we had been basically patching the solutions we had in place in order to basically keep with requirements in terms of relevance, in terms of new features, and so on. And when you go from indexing millions of documents to tens of millions to hundreds of millions, there are things you need to do about it. So first of all, let's look at the size of search engines on different companies. And the numbers that I'm going to share here are either public, and they're basically you can get them on the web. Some of them were public 4 hours ago, and now we got updated data, for example, for Airbnb. I'm going to share that right now. And some of those are not publicly available, and we have our best guess and numbers that we get from contacts that, well, So Netflix is roughly 100K documents, and of course, people in the audience might know exact numbers or might have counter examples of this. One of those was the Airbnb. We thought you guys had 300K documents, and it turns out that it's getting closer to 1 million now. Then we have use cases like eBay with 500 million documents, and then big things like Bing, Google, or Facebook, ranging from hundreds of billions to trillions of documents. And something interesting is that many of them use Lucene, and some of them use custom C++ proprietary solutions. We are kind of in between. We have hundreds of millions of documents. We were using Lucene. We're switching to a new architecture that is based on Lucene with heavy modifications, and we don't know what's ahead. But our best guess at this point is that eventually we'll have to build something custom. So let me tell you a little bit about the features that we had to build into this architecture in order to be able to scale it. First thing is offline index building, basically building on Hadoop. And I'm going to share a little bit why that's important. But basically, we always need to be able to go back to a stable source of truth and be able to rebuild our entire indexes or add features and so on, which is super important. Then we needed live updates at a finer granularity. Updating a document as a whole didn't cut it for us, so we had to come up with a solution that allowed us to change the text of a document without having to reindex the entire document. Then we have static rank and early termination, and the idea there is that for some queries, you pretty much know what you're getting if you just look at the topmost 100 documents, and then you're basically just scanning the long tail for no good reason. So you would like to cut the query short. Then we have faceting, and there's an interesting relationship between early termination and actually faceting, because counting things if you are not looking at them might be tricky. Data distribution, that is something that I will briefly mention, basically how we get the indexes from Hadoop and put them on the serving fleet. And the relevance framework that we had to build that is different from Lucine's and that allows our relevance engineers to actually deliver great relevance with machine learned models and so on. So a little bit about offline indexing and live updates. So let me tell you about LinkedIn data. We have most of online data sets basically in two flavors. We have a real-time change notification stream. Think of a row on a database got updated. We just get a notification that this row changed. And in a very highly normalized world, you don't get the entire document. We just see a little bit of the document. Let's say this member connected to that, or that person is following that company, things like that. One of the challenges we had before is, well, we need to go grab absolutely everything that we need in order to materialize it and then write it as a single update on a Lucene index. And then those data sets that are online are also ETL'd into Hadoop, so basically, if we need to, we can consume the entire data set or join them offline or things like that. And we often rely on derived data. There's data that gets computed offline. We have a great team of data scientists that build awesome features. Compute which are the skills that you might have that you don't even know, which are the companies that you might follow, things like that. Or can come up with very interesting relevance signals about blog posts that were shared on LinkedIn. Well, you can do impression discounting, you can have decay on shares, likes, and so on to basically figure out which is the real importance of those. But those things, if they are time-bound and they have a time decay, cannot be done in real time, right? So there's a need for building an index offline with those rich features and push it to the online world. So let me tell you a little bit about how a Galene index is, what's the layout. It basically has a base index that we generate on Hadoop periodically. It's a single segment of Lucene. So basically, at the end of building each shard, we optimize it. We get a single segment that will ship to the serving fleet. It's immutable. It's on disk. We don't touch it after we build it until we build a new one. And in order to serve it, we mmap it and mlock it. So it's pretty fast. And as I said, it contains features that are computed offline that we couldn't get in online streams just because we don't have the data. That data takes a while to bake. Then we have a live index that is basically updates to documents that happened since the base index was built. Things like new members or this member connected to some other member and so on. And that's an inverted index that has our own format. It's not a Lucene. It sits completely in memory. And basically just contains that, incremental updates in forms of text. And the thing is that can grow and grow and grow. So eventually, what we do is we snapshot the index. Basically, we create an on-disk representation that is with Lucene format. It starts out empty, and I'll show you basically the life cycle of documents. And it's also a single Lucene segment. So every time we flash, we basically put the new updates on the live index with whatever we have on snapshot, fold everything, and ship this new segment. So it's a segment that grows over time until we ship our base index. Just to understand the following diagram, I'm going to share these two little documents. One is a document that contains Jeff, LinkedIn, and some other terms, and the second one contains read, LinkedIn, and some other terms. So if you were to represent it as posting lists and documents, horizontal lines are documents, vertical lines are posting lists, and we can see that document 1 has a hit for Jeff and LinkedIn, and read and LinkedIn are hit for on document 2. And we also have a forward index that we use binary doc values for. Basically contains a mapping from member ID or document ID to a set of data. Now with this, we can see basically what's the layout of base index, snapshot, and live. You can see base index has basically lots and lots and lots of documents, hundreds of millions of documents, lots of posting lists, lots of terms, and forward index for each document. Now, as we get updates, well, I don't think you can see the numbers, but document 3, for example, got an update at some point after the base index was built, and that ended up touching some terms on snapshot. In the same way, document 11 has updates that are only on the live index and haven't been folded back into snapshot, and some of the documents might have updates on both, like 19, I believe it is, that has updates on both. Now, this covers basically for documents that were built on what we call BSL, that are documents that live in the base index with updates on snapshot and live. And it's important to understand that we'll end up with 3 Lucene segments in some sense. One that is a BSL that contains documents that were present on the corpus when we build the base index. Then something we call S2L2, that is another segment that it doesn't have any documents that are on BSL. And then we have the L3, that is a segment that you could look at as a Lucene segment. It's actually not Lucene, that contains documents that were built since the snapshot was generated. So if we think that this is a base index, and we get a batch of updates for documents, you'll see that, well, we need to create an L1 to process the new updates, and we start routing documents. This green document lives in base, so we're good. This new blue document doesn't exist, so it needs to get routed to L3. It's basically a document that doesn't live in any other segment. And this orange is an update to some other document that existed. After a while, we need a snapshot. We create the snapshots and merge documents. And please note that we got snapshot 2 because documents from live need to fold somewhere, and well, there's no snapshot 3, so they get folded into S2. With another bunch of updates, well, you'll see that we need to create an L2 so we can put updates there. A new set of documents, a brand new document with some term updates, and updates to documents on something that was on snapshot and someone was on base. Eventually, those get folded. And the way we execute queries, actually, is basically looking at each row as a Lucene segment, and we have special term queries that can deal with traversing these 3 structures at a time. And then we do the same for S2, L2, and then we have a special algorithm for L3. So that way, we can basically add hits on posting lists on documents, and we can even delete if we need to, just by adding tombstones and so on. So let me tell you a little bit about static rank and early termination. Static rank is basically the global score of a document. And the idea is that each document needs to have a static rank. It's basically a notion of popularity. Think of page rank on search scale, sorry. On web search scale. And sorry about that. Different documents might have the same static rank. So think of a very simple static rank where you rank, I don't know, members by how many connections they have. Well, you might have lots of people with 0 connections, 1 connection, 100 connections, and so on. There are some numbers that definitely are going to be more frequent than others. On BSL, the base index, basically the index of built on Hadoop, knows the static rank for each document. And that static rank will remain constant until we build a new base index. That's a great reason for building a base index if your static rank actually changes a lot. And then snapshot and live need to somehow get a static rank. And the idea there is, since our documents that you've never seen before and you have no way of having a good, meaningful notion of how to sort them, you end up having to decide, OK, are they more important than anything that I've seen before, or are they not? And that's important because of early termination. So the notion of early termination is that as you walk through a segment, you want to stop the query as soon as you are satisfied with the results that you get. And in many cases, you don't need it. And we have use cases where basically our relevance engineers want to go through all the documents and they're happy with it. And then we have some use cases where they say, we're pretty sure that for the 99.9% of the results that we're going to show are actually in the first 1,000 documents. So if you have a query that matches 10 million, just give me the first 1,000 and we're happy. So the idea is that since static rank, let me tell you a little bit, something that I might have forgotten. So documents on the base index are actually sorted by static rank. So the document with Lucene ID 0 will be the one with the highest static rank. And the one at the bottom will have the lowest static rank. So when we walk posting list, we know that the first document ID is basically the one that is the most important in this corpus. OK. So basically, the idea is if new documents are more important than anything that you could have before, you basically need to walk first your snapshot, the snapshot live on BSL, or the other way around. And it's important also to consider that static rank needs to correlate with your notion of score. If for some reason you have a score that doesn't correlate at all with static rank, you'll have to scan everything, or you'll get crappy results. Going forward, what we want to do is build a very efficient custom index in C++. Actually, we have a prototype working. It's almost getting to prod. And we found that it's pretty similar to what Helios Search presented here in this room yesterday. Something you might notice is that I said that we optimize every base index to be a single Lucene segment. That is a problem when you have millions and millions of documents and you're basically on the last phase of your map reduce. It takes a while. So we want to build it so that, if we change and we don't go through that pain, we might be able to build the index in a very more friendly distributed manner. And BSL and this hack of walking different posting lists on different segments works, but we kind of built it as a hack on top of Lucene, right? And it works great for us. It violates some of the principles of IR, like TF, IDF, get not as accurate as they should be. And we want to fix that, but basically building something that really supports the feature. In terms of faceting, and I said that faceting might be a little bit broken with early termination. The types of facets we supported, discover facets. Basically, as we walk posting lists, we discover hits on posting lists and start bucketizing them. Static values, like get me first degree, second degree, third degree, or so on. So we know the predefined set of buckets, and we just bucketize on those as we walk posting lists. Or you can basically specify specific values that you want on your facets, and we just compute those for you without discovering anything. Our legacy stack had no error termination, so we could do that by counting absolutely everything, and counts were accurate. With Galene, we early terminated. We need to predict the values of some facets. And so they become approximate. They're not super accurate, but they're accurate enough so that members or users don't realize that it's a problem. And someone's laughing, and I'm bored. And going forward, well, let me give you an example of something that might not work out with this. Let's say you sort your index based on, your static rank is based on location of your document. So all your documents on the US have higher static ranks than all your documents on some other countries, right? And then you're searching for people that work for a company that has international subsidiaries. So as you walk down the posting list, and if it's a very big company, you'll probably see 1,000 results, 1,000 hits that are all US. So if you extrapolate that, you'll say, well, okay, yeah, everyone in the posting list is US. Okay, this company has millions of members in US. That is not really the case, and it will depend on the distribution of hits on posting lists. So we basically want to encode data on the posting list so that we can make those predictions more accurate. In terms of the relevance framework, basically what the infra team did was build building blocks that support most of the common scoring needs, being training models, shipping models. Models can be tree-based, can be logistic regression, and basically they need to be trained. So we need to gather feedback about results that are clicked, results that are viewed, and so on, and be able to train those models based on data. And actually something cool that you can do is, with your usage patterns, you can predict which is, or test which is the best static rank for your documents so that you can actually shrink your early termination and actually make your queries execute faster. Something that we also wanted to do was allow relevance engineers to add features to the index quickly, basically new fields, new posting list, and building the index weekly or daily in some cases allows them to basically A/B test what happens if I started using new features or not. It wasn't possible with our previous stack. And the idea was that we didn't want relevance engineers to think about the nitty-gritty details of dealing with posting lists and so on. We wanted to decouple that. So what we did was basically provide a query rewriting framework and a scoring framework. There's a merging framework and so on. I'm going to focus on query rewriting now. The idea is that we have a set of chainable rewriters that can be chained one after another. And the idea is they get an input, a raw query, and by inspecting it and using data models, they can expand it in some way. And these data models are actually built by the framework offline as we build the index, so basically they are in sync. After a bunch of steps, we end up with a rewritten query that might be huge. And I'm going to share an example of that real soon. Then we have, given early termination, how the life of a query, basically what's the life cycle of a query within a shard. You get a rewritten query after the rewriting phase, and we go into a loop where we retrieve a document from the index, we score that document, we pass it to a scorer. The scorer will produce a score, and we'll decide if the loop needs to keep going or not. So we store documents on top results and decide if we need to early terminate or not, and keep doing that until the relevance algorithm is happy with what it saw. Then we get top results from a shard. Now, let me tell you a little bit about the first use case that we migrated from our legacy stack to this platform, and that is instant member search. Basically, the type ahead that you get as you start typing on the search box. One of the interesting things that it has is that it supports second-degree lookups. So basically, you can find people in your immediate connections or connections of connections. And in order to do that, what we had to do is encode within the index connections as terms. So the index contains connections, meaning my document, if I'm connected to him, will contain a term set connected to his member ID or document ID, and so on with everyone that I'm connected. As we get a query, we basically augment it through query rewriting to be something like, let's assume that the query is term Diego space boot. It turns out it ends up being term Diego and prefix boot, And actually, for that, we index all prefixes. So we have prefix B, prefix BU, BUT, and so on. So those are huge posting lists. You'd better have early termination on those if you are not restraining but an OR clause of connections. And then we basically build a huge, and it might be massive, Boolean query with connected to this, connected to that, connected to that. And those connections are actually the connections of the viewer, the person running the query. Static rank reflects popularity, which means that if we stop considering your network or your connections for some reason, what you get is basically celebrities, because we just walk Diegos, and well, we'll get Diego Maradona or something like that. No soccer fans in the audience, okay. And then something that we do offline that we cannot do as we go is cluster documents so that we can deal with spell corrections. So a classic example is Shriram's name. There are lots of misspells of Shriram, or actually not misspells, but real spellings of that name that are kind of synonyms. If he introduces himself and he doesn't give you a card or LinkedIn profile or anything like that, you will go start typing on the search box, and I'm sure you'll make a typo. So what we do is we grab tokens and we make clusters out of them that we can then index as posting list, and we can ship as data models to rewriting. So what a rewriting can do is it gets a query, it will expand it as term Shriram or cluster some numbers, 5, 6, 7, 8, and prefix SA, and connect it to this, that, and all your connections. So basically, we can walk a bunch of posting lists and get your results back. So in summary, what we had to do was scale our infra to basically be able to support those kind of use cases with great latency and be able to modify documents as well. Think of adding a connection, right? So what we just do is add a connected to this member or this ID on the live index, and that's all we need to do. We don't need to go and fetch absolutely all connections of a member that might be in the millions. Same thing happens with people following companies or things like that. Sometimes the skew between entities is massive, and there's a very high price that you need to pay if you want to do something like this, indexing documents entirely. Something else that was a win was developer productivity, because we could definitely split between the infra team and the relevance team. We could really work on the platform and make it great, while the relevance team could just work on getting quality results. And we got to result quality scaling by allowing that team to build machine learning models and test them and ship them and A/B test them and with a very fast cadence, like weekly and sometimes even daily. Well, and that's basically it. So thank you all, and I think we have like 2 minutes for questions. Yes.
I have a couple questions.
Yes.
So first, right, so what kind of advantages you're getting from this architecture compared with the Solar out-of-box feature?
So, okay.
Second question is, actually, look at the architecture. What's the basic functions from the same?
Okay. So 2 questions. What do we get out of this architecture that we don't get from out-of-the-box Solar? And which pieces of Lucene we kept, I guess. Okay, so let me start with the second question. What we kept from Lucene is basically the on-disk format, the codecs for writing posting lists into the index, and that's pretty much it. In terms of what we can do that Solar can, well, a problem that basically one of the walls we hit was that as documents grow and grow and grow, and you start adding more more features, basically think of we're denormalizing lots of tables into an index, right? it stops being cost-effective to go fetch absolutely all data and write it back, especially with entities that change a lot, right? So a group that has lots of members joining it, or companies that are being followed, or things like that, it's not cost-effective. Yes?
So I was wondering what size is currently of the platform style engineers working on it versus the people who are working on the quality engineering that you were talking about, and how that distribution will change on the new platform.
Okay, so the question is, how big are the teams working on infra and working on relevance, and how we see this shifting as the platform is more mature? I would say at this point, teams are roughly the same size in terms of infra and relevance. And what we want to do is basically make that team more efficient, not have to deal with thinking about how to deploy all this. Actually, I didn't talk about how we deploy everything and basically how automated it is. I wanted to keep it more like Lucene-centric. But we did a lot in terms of making them more productive, being able to ship models fast, things like that. And I'm out of time, but I'm happy to chat offline if someone has questions.